Swayam Prabha. Digital India. Educated India.
LE, everything remains constant. So I will have one pulse which is corresponding to T1 and T4 conduction. This is the current. This is the other current which is corresponding to T2 and T3 conduction. So this is going to be the current I. Right? This is discontinuous. This is clearly discontinuous case. I'm going to leave the continuous case for your exercise. You will do that. Continuous case you should be able to draw. I don't think it should be such a major issue. Right? Please draw it for continuous case. Now let us try to look at the last type of single phase converter, which is semi-controlled. We said uncontrolled when we had all 4 diodes. We said fully controlled when we had all 4 thyristors. We can call it as semi-controlled when we have 2 diodes and 2 thyristors. So we are essentially going to have, let us say, 2 thyristors like this and then 2 diodes like this. I can even draw in one leg both of them thyristor, in the other leg both of them diode. There is nothing wrong. But I want to be uniform over 3-phase and single phase. So in 3-phase, if I am talking about semi-controlled, I have to have 3 on the top probably or at the bottom probably as SCRs, and at the top, if I have assumed SCR, at the bottom I should have all the 3 as diodes. So this is semi-controlled converter, and let me talk about this with RL load. So let me call this as T1. Let me just adhere to the same 4. So I would call this as D4. And this is T2 and this is D3, and I'm going to have the power supply connected here. Right? Let us see now what happens. I don't have to fire D3 or D4, clearly. They are uncontrolled devices. But I necessarily have to fire T1 and T2. Otherwise, they are not going to conduct. So, the tone for the conduction is going to be completely set by the thyristor. At least to start with, the conduction will be dictated by when I am giving the pulses to the thyristor. So let me draw the waveform also, and simultaneously let us try to see how the whole thing is going to work. So this is my power supply, and when I am inverting it or I am rectifying it, I am drawing the other side also like this. Right? I am firing, say, this T1 at some value alpha. Then obviously I have to fire T2 at pi plus alpha for symmetry. So only one device I am firing, obviously. So this is T1 and this is T2. Right. When I am having T1 fired, T1 and the conduction path is somewhat going to be like this. This will go like this. This will come through D4, because D4 hopefully is forward biased. You can check it. And then I'm going to have the current flowing like this. This is how the current will flow. Right? From the power supply, it will go through T1, load, D4 and back to the power supply. That's how it is going to be. So we are essentially going to have a current like this. That means, let us say my current probably would increase slowly depending upon the same equation, Vm sin omega t equal to Ri plus L di by dt. So the same thing holds good when Vm sin omega t equal to Ri, I am going to have the peak being reached. Same thing holds good. So current has reached a peak somewhere here and then it will start falling. Yes. What happens at this point? I have to check. I'm talking about the point here, right? That is pi. The current has been flowing. If the current is flowing, I am going to have this almost as a short circuit, this almost as a short circuit. Am I right? So if this is a short circuit and this is reversing its voltage because omega t is pi already, so I will have plus here and minus here when I am talking about negative half cycle. This plus is connected through D4 to D3 here. This minus is connected here. Whether I like it or not, plus and minus are connected now in such a way that this diode gets forward biased. D4 is conducting. Because of that, the supply voltage comes now across D3. Until pi, the supply voltage was reverse biasing it. The moment it crosses pi and it comes into reverse half cycle, I am going to have essentially D3 getting forward biased. The moment D3 gets forward biased, it's not going to keep quiet. It will start conducting. So D3 will start conducting. The moment D3 starts conducting, now look at this. If D3 is conducting, it becomes a short circuit. D3 jumped into conduction because of D4, because D4 was the one which was instrumental in making D3 forward biased. But the moment D3 gets into conduction, now this is a short circuit. So I can say that this is plus, that plus goes here. And this is anyway connected to minus. So D4 sees that itself is reverse bias. The moment D3 gets into conduction, D4 gets reverse biased because D3 is a short circuit. This minus comes to the anode of D4 and this plus comes to the cathode of D4. So D4 completely is switched off. So I'm going to have, because of this uncontrolled nature of the diodes, previously I was having a clear, distinction between the conduction zone and the non-conduction zone. Whenever I give a gate pulse, only then it will start conducting. Whereas here, the diodes jump into conduction the moment they are forward biased, and the forward biasing and reverse biasing happens because of the supply voltage as long as the current is continuous. If the current is not continuous, this diode would not have been conducting. If the diode is not conducting, I can't talk about this short circuit and so on and so forth. So, whenever I have a semi-controlled converter, especially in the lower portion of the leg, then the negative half cycle almost the control goes for a toss. It is something like that. Whereas what now is going to happen is both these fellows conduct together. T4 has gotten into conduction. T1 is already conducting. Nobody to turn it off. It is, yeah. D3 has gotten into conduction. T1 is also conducting. So this entire leg is conducting, happily circulating a current only through the load and the two short-circuited devices. As simple as that. So the source is completely eliminated. The source is out of circulation. It is not there in the picture at all. So if I look at it from here to here, it is going to be T1 D4. T1 is already conducting. If the any thyristor device is conducting, to turn it off, you have to follow two conditions in sequence. The first and foremost condition has to be the current has to be less than holding current. That's not happening. So, T1 will not care. It will say, as long as I am having the current, I will continue. No. See, the thing is that the moment it conducts, if you forget about the fact that it is ideal, it is not ideal. It will have a resistance, definitely. And the current is flowing in this direction. That will make this slightly positive, that slightly negative. So it is forward biased by virtue of its own voltage drop. It is connected to the negative terminal, but you have to look at this also. At what terminal? See, potential difference we have to look at. We cannot look at only anode potential. With respect to the cathode, whether it is more positive. That's what we have to check. So if the current is already flowing, there is a small voltage drop, 0.7 or 1 volts or whatever. That will always be plus here and minus here. Because thyristor can never conduct in the opposite direction, obviously. Right? So I will have basically from pi until pi plus alpha, T1 and D3 will conduct together. And this is simply going to circulate the current like this. Source current does not exist during that duration. Source is completely isolated. This particular duration is known as the freewheeling duration. It is simply freewheeling the current through the two devices which are connected, continuously in series. So this duration, what we have is freewheeling. Right? Now if you look at, again, the current probably would come down, but not as fast as what it was coming down for the fully controlled converter. In fully controlled converter, this negative portion of the voltage was appearing. That negative portion of the voltage was a huge drain on the inductance stored energy. Please remember, this is still the equation. When I have freewheeling, this will become 0 equal to Ri plus Ldi by dt if I neglect the drops across the two devices. Right? So there is nothing which is actually coming up as source voltage. Whereas in fully controlled converter, this negative portion of the voltage was appearing. Because there is a negative portion of the voltage that is acting like a drain on the inductance stored energy, definitely the current could have fallen faster because it is essentially draining the energy of the inductance. But now the current will not fall as fast. So it is kind of pretty rare to see discontinuous conduction in semi-controlled converters. You will see very rarely discontinuous conduction in semi-controlled converter unless I make my alpha very large. If I make the alpha very large, the conduction itself starts very late, so there will not be much of stored energy and so on. But for smaller alpha, you will hardly ever see discontinuous conduction with RL load. You will not see. Right? If it is only R load, I don't think it makes any difference. Only the inductance stored energy is really creating all this magic. So if you don't have inductance in the load, then all these things are, not valid arguments at all. So if I try to draw the other portion of the current, I should again draw it as though it is increasing and decreasing and so on. This is how the current will be. So this is the DC current or load current. Now if I try to draw the load voltage, until here, I am going to have the load voltage coming up like this completely. But the moment the short circuiting happens, I will have 0 voltage. Again, I will have this voltage appearing. Again, I will have 0 voltage until 2 pi plus alpha. So whatever I have shown here is the load voltage without any negative portion of the voltage. There will not be any negative portion as far as the load side is concerned. So whenever I have a freewheeling diode or freewheeling kind of duration coming into picture, I am going to have zero voltage. Sometimes we tend to put an explicit freewheeling diode despite the fact that these two can very happily do the freewheeling. There is no problem. But we put a freewheeling diode sometimes to reduce the voltage drop. Although we say ideal devices will not have any voltage drop, instead of having two devices having the voltage drop, if I have only one single device having the voltage drop, then the current can even pull along for longer duration. You understand? Because R times I, whatever is the forward resistance of this and forward resistance of this, whereas here there is only one device whose forward resistance needs to be considered. So sometimes we might explicitly put a freewheeling diode just to reduce the drop. What is happening across two devices is a higher drop. I want to reduce the drop, so I might put just one device across this. So now let us look at the supply current waveform. Yes? Inductance was not low, beta. Yeah, very much. But that's why I said in a reasonable value of inductance, if I compare semi-controlled, if I compare fully controlled, semi-controlled has a better possibility of having continuous conduction. I'm comparing those two. Similarly, if I have a much larger alpha, even for a high inductance, I might get into discontinuous conduction. It's very much possible. Right? Yeah. Absolutely. See, most of the times what happens is, we assume everything to be ideal devices and do the analysis completely. And 20 millisecond is vast, like one yug, compared to the kind of microsecond durations that are involved in turning on and turning off. So if you say that D3 is jumping into conduction, even that will take some time. By then D4 would have recovered. So fortunately, in semi-controlled converter, when we operate it in actual practice, we hardly see the supply getting short circuited. You got his question. He was asking basically that, Shikhar, he was asking the question basically that if this is in reverse recovery and this has already jumped into conduction, you are going to short circuit the supply. Right? If you are going to short circuit the supply, then it's not really good for the supply, normally. Yes. And one more thing we have not considered for all the analysis, which I will finally consider. None of the sources are ideal sources. We always consider this to be a very ideal source. There is always an impedance. Right? You have transmission line, you have transformers, you have everything. All of them are going to have some impedance or the other. Right? As long as T1 and D4 are conducting, I am going to have the supply voltage directly connected to the load. So supply voltage comes right across the load. So that's why this is the supply voltage and I'm going to have the load voltage same as supply voltage from alpha to pi. After pi, current is not zero, but these two devices are conducting. The load voltage is this entire thing. The load voltage is this entire thing. So this entire thing is short circuited by two devices. Right? That's the reason why I get zero voltage. And after that, I am again going to have the supply voltage from pi plus alpha to 2 pi. From 2 pi to again 2 pi plus alpha, it will be zero voltage because the other two devices will be short circuited. Right? Now if I look at the supply current. So, from here, it is T1 and D4. So, I am going to have exactly whatever is the DC side load current, the same thing will come. Right? It is exactly the same waveform what I have drawn, I have taken as it is. But from here to here, the supply is isolated completely. The supply is not in the circulation. Only it is going through the two devices through the load. That's it. So, I will not have any supply current during this portion. So, this is starting from alpha until pi. Again in pi plus alpha, I am firing the device which is corresponding to T2. So, T2 and D3 will take over. Whenever T2 and D3 are taking over, the current will flow exactly in the opposite direction. So, I am going to have the same current, what is same as supply current, and then it is somewhat like this. And then here is where is 2 pi. At 2 pi the current ends. And 2 pi to 2 pi plus alpha, it will circulate only through the load. There is nothing returning to the supply. Right? Please do some simulations in PSIM, because this will become your second nature only if you try to look at some of the waveforms clearly. Right? Simple student version will do. For these circuits, that will do. Not a problem. Right? Huh? PSIM. PSIM. It is from PowerSim Incorporated. It's one of the simplest softwares compared to Simulink MATLAB and so on. Right. So much so for semi-controlled converter. I go back here a little bit to talk about, where did I talk about the power factor? Somewhere I talked about power factor. This is one, yeah, here. I talked about power factor somewhere here, or at least the zero crossing of voltage and zero crossing of current I was talking about at this point. So if I actually look at fully controlled converters, supply side current, right? When I didn't have any of these rectifiers, if the supply voltage is sinusoidal, the supply current will be sinusoidal. R, L, C, whatever you connect, it will be good. There is no problem. The moment I connect a power converter and I intervene with the switching of one device, switching off of another device and so on and so forth, the current wave shapes get completely modified. They are far from being sinusoidal. If I have a very high inductance, almost the oscillation will be negligibly small. So if I try to look at the entire current, it will look as though this is like a current like this, and this will be a current like this. If I neglect the ripple, the current will look completely like a rectangular current. Like I will have a square wave or rectangular, whatever you may call it, you will have essentially a current wave shape like this. It is not at all sinusoidal. That's what I'm trying to get at. You guys have learned some Fourier series, right? So you guys can definitely derive the fundamental for a current like this. So if you derive the fundamental for such a current wave shape, I'm talking about a current wave shape somewhat like this. So it is starting from alpha, it is going until pi plus alpha, and this is 2 pi plus alpha. Right? Maybe let me call this as ID, the DC current. That is the magnitude of the current. For this, if I try to derive the fundamental component and then other harmonic components using Fourier expansion, then I would see that the fundamental component I1, let me call that as fundamental component, which is corresponding to 50 Hertz. That will come out to be something like 4ID by pi. Correct me if I am wrong, I don't know. You can derive it anyway. It is approximately 4ID by 5. Not approximately, accurately 4ID by 5. Pi. This is the peak of the fundamental. This is the peak of the fundamental. And fundamental is normally sinusoidal in nature, because Fourier expansion essentially tells you that any periodic waveform can be expanded into several sinusoids consisting of the fundamental, second harmonic, third harmonic, fourth harmonic until nth harmonic. Right? So, if I try to look at the fundamental, it is a sinusoid in its own right and it is going to have the peak value as 4Id by pi. And if I try to draw that fundamental corresponding to this, it may look actually something like this. It should actually have a slightly higher value maybe, and